Since I've talked about aerospace engineering as the conquest of the third dimension, that is, moving away from the surface of the Earth, I'd like to finish this introductory week's lesson with an illustrated journey taking us from the surface of the Earth outwards into space. Here we are in the Hayden Planetarium in Boston's Museum of Science. And there, projected up on the dome, is an image of the planet Earth as we would see it if we were out in space. But until the dawn of the space age, we could only imagine the Earth like this. Throughout human history, we've lived basically in two dimensions. People have looked upwards and dreamed of achieving the freedom to fly through the sky like birds. We have myths and legends of people who accomplished this, like Daedalus and Icarus. Of course, we can climb mountains and take elevators up to the top of tall buildings. But until very recently, human beings could not leave the surface of the Earth. Basically, aerospace engineering is about how we've learned to travel and operate in the third dimension. Some people have a little difficulty grasping the incredible scales that are involved as we leave the Earth and move out into the universe.
Liftoff. We have a liftoff.
How far did astronauts have to travel to get to the moon? How far away is Mars, or the outer planets of our solar system? How far away is the nearest star, or the other stars in our Milky Way galaxy? And how big is the galaxy itself? How far away are other galaxies? And ultimately, what's the size of the universe? It's a tremendous range of scales to go from mountains on the Earth to faraway galaxies. Sometimes it's hard for the human mind to comprehend. But that's what I hope you'll understand. It's what I call the aerospace perspective. Historically, the only way we could move around in the third dimension was to follow the contours of the Earth. Ancient people revered mountains. They thought of them as the home of gods. The Earth's tallest mountains are the 8,000-meter peaks of the high Himalaya. I've trekked in the Himalayas, and when you look up at these huge peaks, it's really hard to believe that the surface of the world is flat. So let's do a little demonstration. Here we are in the Museum of Science in Boston, and here's a globe which has a radius of about 1 meter. We're just watching the high Himalaya come around into view. Now, the vertical scale is exaggerated here by about 40 times, just so visitors can see the mountains and the valleys. But really, if you think about it, the radius of the Earth is 6,400 kilometers. So with the 8-kilometer height of the high Himalayas, that's 1/800th of the radius of the Earth. So for a 1-meter radius, the height of the highest mountain on Earth, Mount Everest, is only about 1 millimeter above sea level. So, although it might be hard to believe if you're gasping for oxygen as you climb through the death zone towards a Himalayan summit, the surface of the Earth really is incredibly flat. Aeronautics is the air part of aerospace, and it all takes place inside the gaseous envelope which surrounds our planet. When you go outside on a clear day and look up at the big blue sky, it looks like it goes on forever. But the atmosphere does not go on forever. It's held to the Earth by gravity, and its pressure at any given altitude depends on how much air is pushing down above it. On the surface, near sea level, this is about 1 kilogram for every square centimeter. And as you rise above the surface, there's less and less air above you pushing down, and so the pressure decreases. Technically speaking, the pressure distribution falls off exponentially with height above the Earth's surface. At 5.5 kilometers, you're already above 1/2 of our atmosphere. On the summit of Mount Everest, at 8.8 kilometers, you've actually gone up 1 scale height, and so the pressure is about 1/3 of the pressure at sea level. There's not enough oxygen up there to sustain life, but airplanes like to fly at these high altitudes because the thin air has less drag, which means they burn less fuel. The highest commercial airplanes fly about 12 kilometers, that's 39,000 feet, which is about 50% higher than Mount Everest. On the scale of this globe, that puts us at a whopping 2 millimeters above sea level. Not a huge jump up into the third dimension. Up here, you're 80% of the way to the top of the lowest level of the Earth's atmosphere, which we call the troposphere. This is the level of the atmosphere where almost all weather phenomena occur. The gaseous area surrounding the planet is divided into several concentric spherical strata, of which the troposphere is the lowest. There's a nice photograph taken from the International Space Station of the space shuttle silhouetted against the different layers of the atmosphere. The stratosphere is the second major layer of air in our atmosphere. It goes up to about 50 kilometers above sea level. About 90% of the ozone in the atmosphere resides in the stratosphere in what we call the ozone layer, which is located at an altitude between roughly 20 and 30 kilometers. The ozone layer absorbs the far ultraviolet radiation from the sun, which would be harmful to life. A few specialized airplanes can fly in the thin air of the lower stratosphere. For research purposes, we launch large helium-filled balloons. The diameter of these giant balloons can be as large as 160 meters, and they reach altitudes of almost 45 kilometers, which puts them above 99% of the Earth's atmosphere. 45 kilometers on the scale of this globe now puts us out at a whole half a centimeter above sea level. Still pretty close to the surface. My earliest research in high-energy astrophysics was actually carried out using high-altitude balloons. I can tell you it was fascinating watching these huge balloons be inflated, lift off the ground, and sail up into the sky. The mesosphere extends from approximately 50 to 80 kilometers. In this region, concentrations of water vapor and ozone are almost negligible. And since water vapor and ozone absorb most of the sun's energy in the troposphere and stratosphere, the temperature in the mesosphere is lower than in those lower layers of the atmosphere. And finally, we get up into the thermosphere. The temperature in the thermosphere generally increases with altitude up to about 1700 degrees Celsius due to the absorption of solar radiation by the remaining gas molecules. The exosphere is the most distant atmospheric region from the Earth's surface. The upper boundary of this layer extends to heights of 1,000 kilometers, and it's relatively undefined. The exosphere is a transitional region between the Earth's atmosphere and interplanetary space. Up here, the air is thin enough that satellites can actually stay in orbit. And with the exception of the Apollo missions to the Moon, this is where all human space activities have taken place. Here's another view of the atmospheric layers as seen from space. I took this picture in which you can see the crescent moon and the planet Jupiter. So, now that we've taken a short trip through the third dimension, off the surface of the Earth and out into space, you should be able to answer a question that I love to ask young students when I go out and talk in schools, and that is, how far away is space? I get all sorts of answers, mostly large numbers like, 1 million miles or so. There is an official definition of where space begins that's recognized by the International Aeronautical Federation. That's 100 kilometers, the famous Von Karman line, about 62 miles. You have to ride a rocket to get up this high, and when you go above this altitude, you're officially entitled to your astronaut wings. On the scale of our globe, that is about 1 1/2 centimeters. That's how high you have to go to become an astronaut.
And we have liftoff.
Of course, I made my trips into space on the space shuttle, and it was really nice for the commanders to call out when we went through 100 kilometers, which they call clicks. They would say for the rookies on board, "Hey guys, 100 clicks, congratulations, you're now full-fledged astronauts." I hope you understand, however, that there really is no abrupt boundary between the atmosphere and outer space. The air just gets thinner and thinner as you go farther away from the Earth's surface. So when you really think about it, space isn't very far away. It's closer than New York City is to Boston, or London is to Paris. At the 100-kilometer Von Karman line, the residual air still creates much too much drag to allow you to stay in orbit. The lowest that the space shuttle ever orbited was a little over 200 kilometers. Here I am doing a spacewalk. The The ground seemed pretty far away from me when I looked down, but now that you understand from an aerospace perspective, you can see that we've barely left the surface of the Earth. So on the scale of our globe, the 400-kilometer high orbit of the International Space Station, which is where the shuttle used to fly, is about 6 centimeters above sea level, about the width of my hand. So when you're up in a shuttle or in the space station, it may look like you're really far above the ground, but really, relatively speaking, this is essentially how close you still are to the Earth. And that's important as part of gaining this aerospace perspective. Here's a graphical view of the altitude of the orbit of the International Space Station compared to the diameter of the Earth. You can see that the space station really isn't that far away from the surface. In our lesson on rocket science, we're going to learn about rocket staging and how it takes at least 2 stages to get from the surface of the Earth up to what we call low Earth orbit, which, as we saw on the scale of this globe, is about 6 centimeters above the surface. Geostationary orbit, on the other hand, is 36,000 kilometers away, and on this scale, that's 5 meters. So let's ignite that imaginary stage and move from low Earth orbit all the way out to geostationary. Here out at 36,000 kilometers, geostationary orbit, our orbital period is 24 hours, the same as the Earth's. So these satellites appear to stay over the same point on the Earth all the time. This is very nice for telecommunications satellites. We have antennas on our buildings and you can just point them at one direction in the sky and you don't have to continually move them. On our journey outward from the Earth, finally, we've moved a significant distance into outer space. The farthest human beings have ever traveled away from the Earth was during the Apollo flights to the Moon from 1969 through 1972. I like to do an experiment with my students to give them an idea of what was really involved in leaving the Earth and traveling all the way to the Moon. We demonstrate this using a model of the Moon. In class, we use a globe with a radius of about 20 centimeters, and you can see that this Moon is about the right size for this scale. I always ask 2 students to participate. Position yourself with the right perspective. The challenge is for them to position themselves so that the Earth and the Moon are the right distance apart, so it's roughly 10 times the diameter of the Earth. And the results can sometimes be amusing. You get the point. The Moon is pretty far away. Big hand for our demonstrators here. The Moon is about 250,000 miles away, roughly 400,000 kilometers. And the circumference of the Earth is about 25,000 miles, or about 40,000 kilometers. So the distance to the Moon is about 10 times the circumference of the Earth. On the scale of our big globe here in the museum, this means about 60 meters away, roughly 200 feet. It took a little while to walk that 60 meters. It took the Apollo astronauts almost 3 days. From that distance, the Earth looked very small indeed, just this beautiful blue marble suspended up in the sky. Only 24 human beings have gone this far, of which 12 actually walked on the surface of the Moon. Compared to all the other distances we've been looking at, it's pretty immense. These days, many people talk of Mars as the next destination for human spaceflight. Well, if you think going to the Moon was hard, that was nothing compared with going to Mars. The closest Mars ever comes to the Earth is about 40 million kilometers, 100 times farther away than the Moon. On the scale of our museum globe, this would be about 6.5 kilometers away. Keep this perspective in mind when you think about human space flights to Mars. Mars is hard. Human exploration of Mars may take place one day, I hope so, but the financial resources needed to accomplish this are beyond what we currently have available now. But our desire to explore can at least partially be satisfied with robotic explorers, such as the 1997 Pathfinder rover. All active exploration in our solar system, that is, where you can physically interact with the local environment, now has to be accomplished with robots. Well, even rovers like to take selfies. Of course, controllers back on Earth had to tell it to do this. Remember now how far away we've come. It takes radio signals tens of minutes to make a round trip between the Earth and Mars. Imagine that you're sitting in a car on the highway, and from the time you turn the steering wheel, it takes 10 minutes until the actual wheels on the car respond. In order to drive safely, you'd have to be going pretty slowly. Here's an image of Victoria Crater on Mars, showing the path taken by the Opportunity rover. The path begins on Sol 951, and the path ends on Sol 1215, 264 Mars days later. Look at the scale on the image. The total distance that the rover covered was about a mile. I mean, you could have walked this path in less than an hour. The smarter we can make the software of our rovers, the more autonomous behavior they're capable of, and the faster they'll be able to go between the times we have to command them. But it's time to leave Mars now and continue our journey outward through the solar system, further expanding our aerospace perspective. We've sent robots much farther than Mars. We've gone to Jupiter to see for the first time close up the satellites discovered by Galileo when he first turned a telescope to the heavens. The Cassini spacecraft has given us a close-up view of Saturn, its satellites, and its spectacular rings. And we can go further out, past the outer planets Uranus and Neptune. In fact, Voyager 2 did this on what was called the Grand Tour of the Outer Planets. The New Horizons spacecraft encounter with Pluto in July of 2015 marks our first exploration of the dwarf planets of the Kuiper Belt, of which Pluto is the nearest to the Sun. Humanity's farthest robotic explorer is Voyager 1, launched in 1977, which flew past Jupiter and Saturn and kept on going towards the outer regions of the solar system. At the end of 2014, Voyager 1 was 130 times farther away from the Sun than the Earth is. The Voyagers are still talking with us, although the speed of light travel time for communicating with them is now about 18 hours. On the scale of our museum globe, that would put the Voyager probe almost 3,000 kilometers away from the museum here in Boston. That's as far away as Denver, Colorado. Our Sun has a magnetic field just as the Earth does. Voyager 1 has now penetrated the boundary from the region of space dominated by our Sun and the farther out reaches of interstellar space, and it's still exploring after all this time. This is an amazing picture taken by Cassini spacecraft's telescopic camera showing some of Saturn's rings and, just above, Alpha Centauri, the nearest star to our Sun. Alpha Centauri is about 40 trillion kilometers away. And at this scale, kilometers don't mean much anymore, so we use light years instead. The distance light travels in a year, which is about 10 million or 10 trillion kilometers. So Alpha Centauri is about 4 light years away. To give you an idea of this vast distance, on the scale of our museum globe, Alpha Centauri would still be more than 6 million kilometers away. That's more than 15 times further away than the Moon. Although Voyager 1 is moving very fast, even if it didn't slow down due to the Sun's gravitational pull, it would take over 100,000 years to reach Alpha Centauri. One of the triumphs of 20th century astronomy was to unravel the structure of our Milky Way galaxy. We now understand that Alpha Centauri and all the other stars that we can see in all directions when we look in the sky at night, they're all relatively close to the Sun. All other stars are concentrated in the Milky Way, which wasn't understood to be made of individual stars until Galileo first observed it with a telescope. This is the Andromeda Nebula, the farthest object the human eye can see. It's about 2 million light years away. Using it as an analogy for our own galaxy as seen from outside, we see that our solar system is located in a small spiral arm about 2/3 of the distance from the galactic center to the outer rim. Thanks to modern astronomical tools such as the Hubble Space Telescope, we can now see much farther than we could ever see with our naked eyes. Hubble is a great example of how scientists and engineers have to work together to create and operate new scientific projects. We're going to jump to the end game now, the farthest that humans have ever looked outward in space. The Hubble Space Telescope and its partner telescopes can show us our universe out to distances of billions of light years. And since light travels with a finite speed, the universe we see when we look this far away is the universe as it existed billions of years ago. So our journey into space, which I originally described as the conquest of the third dimension, now moves into the fourth dimension of time. The domain of aerospace engineering extends from our atmosphere outward to the farthest reaches of the universe. This image to me represents very strongly the aerospace perspective. See how the accomplishments of space technology have allowed us to see things from a totally different perspective. Look at the sun closely and think about how it might look different from any time you've seen it before. Never mind the rays coming out of it, they're artifacts of the camera lens. Look for something more fundamental. You are looking at the sun in a black sky. You've never seen that before. We see the stars at night, but during the day our atmosphere scatters blue light from the sun to make the sky appear bright blue. From the aerospace perspective, the sun truly is a star. It's just so close to us that it's far brighter and larger than any other star in the sky.
KKT, I'm ready to go. I have it. You have it.
Space is indeed another realm of existence for humans. Aerospace engineers should be proud that advances in space technology have enabled many great scientific discoveries. What's amazing is how rapidly we've progressed from humanity's earliest experiments in flight to our voyages to the moon. And in doing so, we fulfilled the ancient dream of flight, of going higher and faster and farther.
Houston, Discovery, roll program.
If any of you students go on to engineering careers, which I hope will be the case, there may be times when you feel frustrated, spending countless hours at your computer solving technical problems. For those times, let me just advise you, don't lose sight of the big picture. Remember that the reason you became an aerospace engineer was because you dreamed of flight.
A new era of American space exploration.
Never, never forget your dreams. Well, we've come to the end of the first week of 1600X, an introduction to aerospace engineering. Next week, we're going to get a little more technical and start to learn about the incredible machines that allow us to fulfill our dreams of leaving the Earth and flying into space. We're going to enter the world of rocket science.